Human decision making is seldom based purely on data and facts, and it is very heavily influenced by our emotions, our memory, and our instincts. And what is interesting about our chief guest for this evening is that he delves deep into the rhythms and the instincts to further his own mathematical theories. Here's a video about him. Can we roll this video, please?
Mathematics, the queen of science? Or is it art in disguise? Our chief guest today is someone who practices math like an art. He believes that the left and the right brain work together to understand the beauty of numbers. He believes in an education that marries aesthetics with science and is himself a product of the Indian liberal arts system. He saw the beauty of numbers not in his math texts, but in the ancient Sanskrit poetry, which he studied under the tutelage of his grandfather, a Sanskrit scholar. In the rhythms of the tabla, which he learned from the maestro Zakir Hussain, he found not just music, but inspiration. And so, it's no surprise that he often turns to these creative outlets when a mathematical problem bogs him down. Taking this approach into his teaching, he explains mathematical equations to his students using the rhythms of the tabla along with Hemachandra's Sanskrit poetry. His creative genius has spilled onto yet another canvas. He's one of the producers of the British biopic, The Man Who Knew Infinity, a film about the Indian mathematical genius Srinivasa Ramanujam. Our chief guest today is recognized worldwide as one of the leading experts in number theory. He is the first person of Indian origin to receive the Fields Medal in 2014. He has also received the Infosys Prize in 2012 along with numerous other accolades. We are honored to have with us Professor Manjul Bhargava.
And may I now call upon Mr. Narayana Murthy to formally introduce our chief guest. Mr. Murthy?
It was about 8 years ago that a bright Princeton junior in mathematics who was interning at Infosys sent me a mail wanting to show me some advanced card magic. I invited her to have lunch with me, and the lunch was indeed much fun. She was utterly excited about the tricks she showed me. When I asked her where she learned it, she told me with much pride that she learned them in her mathematics class at Princeton, taught by a brilliant professor of Indian origin. Interestingly, the same evening, I got an excited call from my son, who was then doing his postdoctoral work in computer science at MIT, that he met a person who became a full professor with tenure at the age of 28 within 18 months of completing his PhD. Not just that, he went on to add that this interesting person could speak eloquently about the mathematics of tabla and recite ancient Sanskrit poetry with error-correcting codes and mechanisms. As luck would have it for me, Professor Srinivasa Varadan chose him as the Infosys Prize winner a few months later in 2012, and we all got to meet him. Professor Manjul Bhargava's PhD thesis under the legendary Andrew Wiles, of course, of the Fermat's lost theorem fame, simplified a 200-year-old number theory law on higher compositions by Carl Friedrich Gauss, with the help of the work of Brahmagupta, an Indian mathematician of the 6th century AD, and as well as with the theory behind the popular Rubik's Cube. Professor Manjul Bhargava is the Brandon Fradd Professor of Mathematics at Princeton University and the first distinguished chair for the public dissemination of mathematics at the National Museum of Mathematics in New York City. He also holds adjunct positions at TFR and IIT Bombay. Professor Bhargava has received numerous awards and honors for his research work, including the Shastra Ramanujan Prize, the Packard Fellowship, the Clay Research Award, the AMS Cole Prize, the Fermat Prize, and of course the Infosys Prize. He has been elected to the US National Academy of Sciences and to all the 3 science academies in India. He has received several honorary doctorates from around the world. He received the Fields Medal, the highest honor in mathematics, in 2014. He is the first person of Indian origin to receive this honor. He received Padma Bhushan from the President of India in 2015 and the Rajasthan Ratna, the highest civilian honor, from the Governor of Rajasthan in 2016. While his thoughts are indeed profound and inexpressibly deep, he is totally comfortable with hoi polloi like me discussing how to make jolada roti or bisibele huliyanna. Just as Kurt Gödel's work on undecidable propositions of Principia Mathematica and related systems enthused Alonzo Church as well as Alan Turing to lay the theoretical foundations for the computer industry, I hope Manjul's current and future work on number theory will create huge opportunities for a large number of Indian youngsters to add value to India and global market. Ladies and gentlemen, I have immense pleasure in presenting Professor Manjul Bhargava to you.
Well, thank you very much. First of all, thank you so much to Sri Murthy-ji for that embarrassing introduction. Very kind. Thank you so much. It's also a really great honor to be here at this Infosys Prize presentation ceremony. Again, 6 years after I was first here for it. It's a really great honor. I want to begin by congratulating today's incredible prize winners. And of course, thanking and saluting the Infosys Science Foundation for the incredible work that it's doing in encouraging and inspiring and enabling these amazing researchers to do and to continue to do incredible research. What's even more amazing about what the Infosys Science Foundation is doing, of course, is enabling young people around the country to learn about some of the best research that's happening in India and globally, in the hopes that it may inspire them one day to enter and pursue their own research. And so, on behalf of all researchers and scientists around the world, I just want to thank and salute the Infosys Science Foundation for this incredible work that it's doing. Thank you so much. So what I was asked to talk about today is a little bit about my own journey in mathematics and what excited and inspired me growing up and deciding to become a mathematician. And in one word, the answer to that is patterns. The beautiful patterns that we see in the world around us, in numbers, and in nature. And so I thought today I'd maybe share a few tidbits, a few examples of such patterns that inspired me to go into mathematics, and that really excited me in wanting to become a mathematician. So to me, mathematics really is the study, the search for patterns. And also, of course, for the explanations as to why those patterns exist. So we want to understand what patterns are there, but we want to understand why they're there. And that's what really the goal of mathematicians is. And of course, once one has those explanations, they can often be used beyond the context in which they were discovered to help propel humanity forward. So examples, for example, there are patterns in the motion of planets, and those patterns led humanity to the discovery and the theory of gravitation, which allows us now to launch our own satellites. Nowadays, it's very important to understand patterns in genomes, which can help in curing disease. And overall, the whole area of data analysis, big data, is about the understanding, the search for patterns so that we can solve humanity's important problems. And so this is what mathematics has always been about, but it's becoming more and more important than ever before, to understand and explain the patterns around us. Now, the area that I work in personally is number theory. And for number theorists, we're interested in patterns of a specific kind, namely patterns in the universe of whole numbers. So for number theorists, our entire universe that we truly care about is the universe of whole numbers. And what are whole numbers? Whole numbers are just the numbers that we use to count every day, 1, 2, 3, 4. And as Brahmagupta told us, we should also include 0 and -1 and -2 and so on. These are the whole numbers. And number theorists are interested in understanding patterns in the whole numbers, in solving equations in the whole numbers. It's the branch of mathematics where this is our universe. That universe of whole numbers seems so simple. It's just our counting numbers, our simple counting numbers. And yet, there is tremendous complexity, and more open questions every day are encountered by number theorists. And so I thought I'll tell you a few of the kinds of questions that come up in number theory today. Maybe the simplest example of the kind of thing that number theorists study are number sequences. Number sequences are among the most basic patterns that mathematicians, and in particular number theorists, study. You've all seen number sequences before. I'll show you a few examples. So here are some examples of number sequences. You've all seen this sequence. Everyone see the pattern there? This is called the all ones sequence. It's a very important sequence in mathematics. There's also, this is called the counting sequence. These are the numbers that we use to count. So these are the counting numbers. Okay, here's maybe the first non-trivial sequence that everyone encounters. These are called the odd numbers. That's right. This is the sequence of odd numbers. It has a complement, which is called the sequence of even numbers. What is this sequence here? This is the sequence of square numbers. Square numbers, even today, are heavily studied. Their properties are not very well known. What are these numbers? These are the cubes. That's right. So up to now, what we've been seeing are sequences that illustrate what is called linear growth or polynomial growth. Another important class of sequences are those that exhibit exponential growth. This here is the sequence of, these are called the powers of 2. You start with 1 and you keep doubling it, right? So you have 1, 2, and then 4, 8, 16. Each time we're doubling, those are called the powers of 2. If instead of doubling, we're quadrupling each time, what do we get? We get the powers of 4. So these two sequences are examples of exponential growth. So these are all sequences that we learn in school. We're taught them, we memorize them. But one thing that doesn't happen in school is the amazing phenomenon that a lot of these sequences are related. And the relations among sequences is actually what really excites. Surprising relations, especially, are what excite number theorists and what excite mathematicians. So some of you may have seen this, but most schools do not ever show this, the fact that many of these sequences are related in unexpected ways. So here's one simple example. It turns out that the odd numbers and the square numbers are naturally related. Okay, those are two sequences that we all learn, but many times it's not told to us. We don't get the opportunity to discover it, that the odd numbers and the square numbers are related. And how are they related? Well, what happens when you start from 1 and adding up odd numbers? So say we start with 1 and add up to 1. Well, we get 1. Okay, but what happens if we add all the odd numbers up to 3? Well, 1 plus 3 is 4. Okay, what happens if we start with 1 and add all the odd numbers up to 5? Well, 1 plus 3 plus 5 is 9. What's 1 plus 3 plus 5 plus 7? 16, and so on. Turns out that if you take the first n odd numbers and you add them up, you get the nth square number. Simple relation among those two sequences. Most students never get to learn that. Very, very fundamental. So the statement is that if you take the first n odd numbers and you add them up, you get the nth square number. Beautiful relation between two sequences that we all learn. And this is the kind of thing that I really feel that should be taught in school. This, first, to discover this pattern, and secondly, once that pattern is discovered, what do we want to do next? We want to understand why. Why does that happen? Why is this happening? Why, when we add up odd numbers, do we get square numbers? And when that understanding happens, it opens up all sorts of other avenues, all sorts of new questions. I try giving this example to school students all the time, and what's amazing is that every student comes up with their own solution as to why it's true. And that's what's amazing about mathematics. Everyone can come up with different solutions, but the answer in the end, they'll all meet at the same answer. And that process of discovery is what makes mathematics so exciting. I'll show you my favorite reason for why this is true. My favorite reason involves a picture. A picture can explain why, when you add odd numbers, starting with 1, you start getting square numbers. And here's the picture. Just want you to look at that a second. So there you see a 6 by 6 grid of dots. And therefore, the total number of dots is a square number, namely 6 times 6, or 36. And why is 36 the sum of the first 6 odd numbers? Well, you can see here in the bottom left corner, we have 1 dot. So what we've done is we've taken that 6 by 6 grid and divided it up into L's, into L-shaped regions. And each of those L-shaped regions are getting bigger and bigger. And how many dots are in each L-shaped region? Well, the first one has 1, the next one has 3, the next one has 5, the next one has 7, and so on. And therefore, when you add 1 plus 3 plus 5 plus 7 plus 9, and all the way up to the 6th odd number, right, which is 11, you get 36. And this argument is completely general. If you took any n by n grid of dots, you can see that if you start making these L's, you'll get n odd numbers, and if you sum those first n odd numbers, you'll get the total grid, which has n squared dots in it. And therefore, the sum of the first n odd numbers is the nth square number. A picture completely explains it, and now once you've seen this, you'll never forget this fact. So the picture immediately shows that 1 plus 3 plus 5 plus dot 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 plus the nth odd number, which is 2n minus 1, is equal to n squared. And that's the kind of proof. Proof is often very scary to students when you say the word proof. This is the proof. It's a proof without words, but it's a proof. And a proof is just something that explains why something is true. And when you understand why something is true, that is the moment where you really understand and when you can start to apply it in other situations. This argument, which is called a proof without words, the analog of this argument can be used to solve many, many mathematical problems. And it's a kind of idea that I use in my own research still today. So to give you just another example, a puzzle for you. So what happens if you take the counting numbers? The counting numbers are also related to the square numbers. What happens if you take the counting numbers and you start adding with 1, and add 2, add 3, add 4, and go up to a certain point, and then go back down and add all those numbers? What do you get? So for example, if you go up to 1 and then come back down, well, you just get 1. Okay. But what happens if you add 1 and then 2 and then go back down to 1? You add it, what do you get? You get 4. What happens if you go 1 plus 2 plus 3 all the way up to 3 and then back down, plus 2 plus 1? What do you get? 9. 1 plus 2 plus 3 plus 4 plus 3 plus 2 plus 1. What do you get then? 16. There's another way of generating the square numbers, this time from the counting numbers instead of from the odd numbers. And why is that true? Well, it turns out you can make a similar pictorial proof. So the general conjecture now is that if you take all the numbers and add up to n, and then go back down and add all the way down to 1, what do you get? You get the nth square number, n squared. And again, the question is, why is that true? That's my puzzle to you to think about when you're bored in this lecture. A similar picture will explain this phenomenon as well. I want to tell you what my favorite problem was as a child, which was stacking oranges. This is the first math problem that I ever solved, and so it's very close to me. Thought I'd share that with you. My mom, who's here today in the front row, she used to buy oranges. She was a great encouragement to me in mathematics, but when she was buying oranges, she was intending them to be eaten. I thought they had other better uses, namely to stack them into pyramids. So if you buy oranges in the store, you often see that oranges are stacked in triangular pyramids. And I enjoyed trying to reproduce these pyramids at home. And the problem that I wanted to solve was the following, was if you make a pyramid of oranges with n oranges on a side, how many total oranges do you need to complete the pyramid? So for example, this pyramid here has 4 oranges on each side, and it turns out to make that pyramid, you need exactly 20 oranges. The number of oranges you need to make a pyramid that has just one orange on each side is of course just 1 orange. If you want to make one that's too high, you'll notice that you need 3 oranges on the bottom, right? And then 1 orange is right on top of it, so you need 4. And then if you have 3 oranges on a side, you need 10. As we already saw, if you have 4 oranges on a side, you need 20. And the sequence continues. I used to ask my mom to get more and more oranges so I could get up to 120. She was not so happy about that. So I made this sequence, and I wanted to know what is the formula for the nth term? In other words, how many oranges do you need if there are n oranges on each side? What is the formula for the nth term? And as I said, this is something that I thought about for weeks. And I must have been in 3rd or 4th grade, and this became my favorite problem. And when I finally solved it, several weeks later, with an argument that's actually very reminiscent of the pictures I showed you on the previous slide, the answer is n times n plus 1 times n plus 2 divided by 6. That's the answer for the nth term. So for example, if you plug in 4, right, you have 4 times 5 times 6 divided by 6, which is just 4 times 5, which is 20. I found that amazing, that I could just ask for 20 oranges, and I could predict in advance that if I made a pyramid with 4 oranges on each side, when that last orange would be left, it would go and come perfectly just on the top. That predictive power of mathematics was incredibly exciting to me. The fact that you could just reason your way to understanding how to solve that problem was incredibly exciting to me. And this was definitely one of the problems that inspired me into mathematics, and the first problem that I ever got to solve. I urge you to think about it too. How does one come up pictorially with that answer? One other sequence that really inspired me, which came up in that video that was shown earlier, the most common number sequence in nature is this sequence: 1, 2, 3, 5, 8, 13, 21, 34, and so on. These numbers are now called the Virahanga numbers. You may have seen them under a different name in school. So they're called the Virahanga numbers because back in around the year 700, Virahanga wrote the following poem, which I'm translating, to a problem that he had posed about counting meters in Sanskrit poetry. So he wrote this poem. He said, write down the numbers 1 and 2. And then each subsequent number that you write down should be the sum of the previous 2. Okay? So that's how this sequence is made. So, right, you write down the numbers 1 and 2, and then the next number you write down is the sum of the previous 2 numbers. So 3 is 1 plus 2, and then 5 is 2 plus 3, and then 8 is 3 plus 5, and then 13 is 5 plus 8, right? And then 21 is 8 plus 13, and so on. You just keep adding the previous 2 numbers. So this was written in a poem back in the year around 700 by Virahanga. Now, Virahanga was not a mathematician. He didn't consider himself a mathematician. He considered himself a linguist, which really illustrates the fine line between science and humanities, between mathematics and the humanities, that this very important sequence that plays a huge role in mathematics and throughout science was actually discovered for the first time in history by somebody who was a poet. So I first learned of these numbers from my linguist and Sanskritist grandfather as the Hemachandra numbers. Hemachandra wrote about these numbers extensively as well in the context of poetry. He lived around the year 1150, and so they commonly became known as the Hemachandra numbers. But now, as we're digging into the literature, we're finding older references. So Virahanka so far is the earliest reference in Indian literature where these numbers came up, and in world literature. These numbers were also written about by Gopala in the year 1135. Of course, in India, these numbers are known as the Fibonacci numbers, after the Italian mathematician who lived 500 years after Virahanka. So the question is, why did Virahanka come up with these numbers in the context of poetry? In school, we learn about them as the Fibonacci numbers, which is kind of the story that Fibonacci made in order to talk about these numbers was this incestuous problem about rabbits, which does not mimic reality in any way. And yet we learn about that, and yet these numbers were actually discovered in an incredible context in poetry, which still have applications today. So the reason Sanskrit linguists were interested in these numbers is because of the way Sanskrit poetry is structured. Sanskrit poetry consists of short syllables and long syllables, and what's special about the way it's pronounced is that when a long syllable comes, it takes 2 beats of time to say. When a short syllable is pronounced, it takes 1 beat of time to say. So a long syllable is exactly twice as long as a short syllable. And so a long syllable lasts 2 beats, a short syllable lasts 1 beat. And so the question that Virahanka and many linguists throughout the history of Indian literature considered was the problem of how many rhythms, how many poetic meters can there be, say, of 8 beats consisting of long and short syllables, where a long takes 2 beats and a short takes 1 beat. Okay? So if you have 8 beats and you need to fill it with longs and shorts, and a long takes 2 beats and a short takes 1 beat, how many ways can you fill in those 8 beats with longs and shorts? So for example, to get 8 beats, you could do long, 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 right? That's 8 beats. Or you could do short, 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 short. Or you could do various things in between. For example, you could do short, long, long, short, long, long, short, short, long. So those are all ways of making 8 beats. And the question is, how many total ways can you fill up those 8 beats with longs and shorts? And the answer, it turns out, comes from the Virahanka numbers, which is why Virahanka defined these numbers in the first place. So if you write down the Virahanka numbers, to figure out the number of ways that you can fill in 8 beats with longs and shorts, all you have to do is go to the 8th number in the sequence, and that's 34. So it turns out there are 34 ways of filling 8 beats with longs and shorts. And now the question is, why is that true? And the answer for why that is true is also written in beautiful poetry by Virahanka and many later writers. And I urge you to think about why this is true. Their poem was just one line to explain it, so you just have to find the right line to explain why it's true. But this is one beautiful example of how a sequence that arose in the humanities eventually revolutionized science. Why are these numbers important today? Well, they occur all over nature. For example, if you look at daisies, daisies tend to have a Virahanka number of petals. This daisy here, you'll see has 13 petals. This one has 21 petals. And this whole garden here has 34, all of these flowers here have 34 petals. And that's kind of amazing. We see these number 34 in nature in this natural way, when that number 34, humans came up with it in the context of poetry. Those kinds of beautiful connections are what really excite mathematicians. By the way, I know that all these flowers have 34 petals because I actually sat there and counted them. Another place where these numbers occur in nature are on, well, basically anything in nature that grows in spiral patterns where nature is trying to pack things as efficiently as possible. So a pine cone is an example. This is the back of a pine cone, and if you count the number of spirals, turns out the number of spirals is always a Virahanka number. Of course, you can count spirals in 2 ways. You can count counterclockwise or clockwise. And it turns out, you can prove this mathematically, that no matter which way you count, you will always get a Virahanka number. So for example, if you count the spirals going counterclockwise here, you can see there that there are 13 spirals on this pine cone. And if you count them clockwise, there are 8 spirals. So 8 and 13 are consecutive Virahanka numbers. And that will be true on any pine cone that you take. Some pine cones have 13 and 21. The really big ones also have 21 and 34. So again, these numbers came up in the context of the humanities, but they've been known by nature for years. And to understand nature, we really have to understand these numbers. Okay, I want to tell you the most beloved sequence for number theorists. the ones that number theorists thought have no applications, and that's why they loved it so much. The Vierhunka numbers have had so many applications. Prime numbers, they thought they'll never have applications. So this is the sequence, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. This is the beloved sequence of prime numbers. So what are prime numbers? A prime number is a number that can't be decomposed any further. You can't multiply two numbers to get that prime number unless one of those numbers is 1. So 7 is a prime number because it only can be expressed as 1 times 7, but no other way. It's an ancient fact due to Euclid that there are infinitely many prime numbers, but once you start asking questions beyond that, we get into unsolved territory. For example, how many prime numbers are there up to a billion? How many prime numbers are there up to 10 to the 40? Exact formulas for that are not known. For number theorists, these are the most beloved numbers because they form the atoms of our universe. Remember, our universe is the universe of whole numbers. And prime numbers form the atoms of this universe in the sense that every positive whole number can be expressed in a unique way by multiplying together prime numbers. So if you take any positive whole numbers, you'll always be able to decompose it into prime numbers, and those will be its constituent pieces, which we consider as the atoms that make up that particle, which is the number. So for example, if you take the number, say 364, you can write that as a product of prime numbers as follows, 2 times 2 times 7 times 13. And that's the unique way that you can write that number. So it decomposes uniquely into prime numbers. All numbers decompose uniquely into prime numbers, and that's why they're the atoms of our universe. And this is perhaps the greatest studied sequence in number theory, and one that I study a lot in my own research. What's kind of amazing in this case too, though, what we've learned in recent decades, is that prime numbers were not discovered by humans. They've been known by nature way before humans. So prime numbers may be the fundamental objects of the world of numbers, whole numbers, which we consider a human invention sometimes, but it's not. It might come as a surprise that prime numbers also arise in nature. These critters here, this insect is called a cicada. It has over 200 species around the world, 200 species of cicadas. About 100 of them, more than 100 of them live in India. And they're actually endangered. Many species of cicadas are endangered because of human population growth and deforestation. But these cicadas are very smart in that they've known about prime numbers way, way before humans. So why is that? Why do I say that? Well, cicadas mostly live underground, but they emerge once every n years. And that value of n always tends to be a prime number, like 13 or 17. So in Princeton, we have 2 species of cicadas. One comes out every 13 years, one comes out every 17 years. India has many species of cicadas that come out every 7 years. And some come out even every 19 years, but they always tend to come out every prime number of years. And this discovery was something that was really remarkable when it first came up, that prime numbers were existing in nature. And why? That was a question. Why did cicadas love prime numbers so much? And how did they discover them? That's a question. And the answer, of course, it comes from evolutionary biology. Why would a cicada want to come out every prime number of years? Well, they want to minimize the number of, if there are predators that come out every 5 years or every 3 years, by coming out every prime number of years, they minimize the chance of being destroyed by their predators. So the evolutionary reason, the hypothesis is that n is least likely to be, when n is prime, it's least likely to be a multiple of the length of a predator's population cycle, which could kill them off. And so those cicadas that were coming out every 12 years, they were probably killed off by predator cycles of 4 and 3 and 6 and 2 years. But those that were coming out every 13 years avoided that fate, and they're still around. And that's why we have cicadas coming out every prime numbers of years. In modern times, of course, prime numbers play a role in our everyday life due to the following fact. So it used to be thought that prime numbers would have no human applications. We were studying prime numbers as number theorists for thousands of years because we just thought they're beautiful, they're the atoms of our universe, we should understand our universe, and so we should understand prime numbers. But we never thought as number theorists for centuries that they would ever have an application to human life. And today, prime numbers are basically entering everyone's life every day, although most people are generally unaware of it. But the reason they come up every day in modern times is due to the following fact. Suppose you have say 200-digit prime numbers Okay, so really big prime numbers, and they're easy to make. They're algorithms that can produce such 200-digit numbers in a matter of seconds. So suppose you have two 200-digit prime numbers, and you give a computer to multiply those two 200-digit prime numbers. It turns out any computer can multiply those two huge prime numbers in a fraction of a second and immediately give the resulting roughly 400-digit answer. But suppose now you took that 400-digit answer and gave it to another computer and said, find those original two 200-digit numbers that were multiplied to get that number. Okay? So if you gave this 400-digit answer to another computer and asked it to find the original two 200-digit numbers, the best known algorithms working on all the world's best computers would not be able to find the answer for billions of years. And that's kind of shocking, right? Because one way, multiplying, you could just do in a matter of seconds, and then you ask all the world's computers, all the rest of the world's computers to find the original two 200-digit parts, and nobody knows how to, not the best computers working for billions of years can do it. This is one of the major open problems in number theory, one that I often think about as well. It remains unsolved, and because it's unsolved, people who do cryptography and make codes for secure communications thought, well, since number theorists couldn't solve this problem for 2,000 years, maybe it's hard, let's use it to encrypt. And so much of the world's security is now based on the fact that we can quickly multiply two huge prime numbers, but we can't go the other way. Often when we submit private information on the internet, for example, when you buy something with your credit card on the internet, what is keeping your credit card number secure is actually this fact, that it's easy to multiply two huge prime numbers, but it's hard to go the other way. Now, I should be clear here that just because number theorists have not been able to solve this problem, as far as we know, doesn't mean that there isn't some government or some corporation out there that secretly knows how to do it. So it is possible that there is someone out there that's reading all our credit card numbers. So since no one knows how to factor numbers, or so we think, this method of encryption is presumably secure, but we don't know for sure. And that's why it's become even more important and become one of the really fundamental problems in number theory, and why it's become one of the most heavily funded branches of mathematics, when it used to be considered just this number theory used to just be considered this pure branch of mathematics that people do for fun, and now 2,000 years of number theory is now being used to keep our nation and the world secure. But because we're not sure that no one knows how to solve it, one of the most fundamental problems in number theory has now become to either prove that it's impossible to go backwards, right, to find the original two 200-digit numbers, or to find a quick way to do it so that people stop using it. So this has become one of the most fundamental problems in number theory, the problem of factoring, the opposite of multiplication. But as far as we know, it remains an unsolved problem. And since our security depends on it, it's very, very important that we get to the bottom of this, and that's why it's one of the most important problems in number theory. Okay, I'll tell you one last tidbit that has to do with prime numbers. This is a number that I feel everyone should know about. When I first learned about it as a child, I was completely blown away. How many people have seen the number 142,857? No, hardly anyone. I claim it's a very, very special number. And the reason it's special is that if you take 142,857 and multiply it by 1, you get itself back. Okay, maybe that alone isn't very special. But what starts to make it special, now we've multiplied it by 1 and we got the same thing back. What happens if we multiply it by 2? 142,857 times 2 is 285,714. The same digits were just cyclically moved around. What happens if we multiply it by 3? It turns out we get 428,571. What happens if we multiply it by 4? We get 571,428. What happens if we multiply it by 5? 714,285. And finally, what happens if we multiply it by 6? We get 857,142. Isn't that amazing? This is a pattern that's been noted by number theorists for a long time, and it has very deep reasons for why it occurs. It's not just a purely recreational thing. So what happened is that we took a 6-digit number, we multiplied by 1, 2, 3, 4, 5, and 6, and we got all cyclic rotations of the number that we could possibly get as the first 6 multiples of the number. So Numbers like this are called cyclic numbers because their first multiples just cycle the digits around. And the question is, a natural question that any number theorist would then ask, is are there other such numbers? Are there n-digit numbers such that if you multiply by 1, by 2, by 3, all the way up to n, you just get all the cyclic rotations of that number back? 1, 4, 2, 8, 5, 7 is one such number for n equals 6, right? It's a 6-digit number. And the question is, are there other such numbers that have more digits that you just get all the cyclic rotations when you take the first n multiples, if it has n digits? So are there other such n-digit numbers so that if you multiply by 1 through n, the number just cycles around over and over? And it turns out the answer is yes, there are other such numbers. I'll give you one more example. The next, so that 16-digit number there also has that property. So if I urge you to take a picture, I see many people taking a picture of that. Put it on your iPhone calculator, multiply by 1 through 16, and you'll find that this number just cycles around over and over and over 16 times. Okay, so there are other such numbers. And now the question is, are there infinitely many such numbers? That's the next number. That's the next question that any number theorist would ask. And embarrassingly enough, number theorists have studied this kind of question for decades, and it's an unsolved problem. Are there infinitely many such numbers? There is a famous conjecture, and a conjecture that's very close to my heart. I think about it a lot because it has many, many consequences for the kinds of problems that I think about. It's called Artin's conjecture. Artin's conjecture is a far-reaching conjecture in number theory that if it was true, it would imply that there are infinitely many such numbers of larger and larger numbers of digits. And Artin's conjecture also predicts how often these numbers occur. And so I wanted to give this example because this really shows that recreational mathematics and deep mathematics are not separate. All mathematics is recreational when you look at it the right way. I won't get to talk about why this happens, but number theorists understand why this happens. And it's kind of related to self-similarity in fractals. Everyone's seen fractals before. A fractal is an object that looks like itself if you zoom in. And one of the most beautiful examples of a fractal occurs in nature in this fern. This fern here, if you look at this fern, if you zoom in and just look at this leaf here, that's a copy of itself. And then if you look at one of its leaves, that's another copy of itself. And that happens for several iterations. And theoretically, it happens to infinity. That if you keep zooming in, you just keep seeing the same object over and over again. That's what a fractal is. And such phenomena of fractal occur all through nature, in snowflakes, leaves, clouds, coastlines, in mountains, in lightning. And what's amazing is that this notion of fractal has something to do with that number 142,857 that I told you before. Those are the kinds of beautiful connections that inspire mathematicians. Fractals have existed. Perhaps the first time they existed in architecture was in India. All through ancient Indian architecture, one sees examples of fractals. This temple here, for example, if you keep zooming in, you just see copies, again, of the same temple. If you zoom in here, this is a copy of the temple, and then you can't see it. But if you zoom in to one of those things, it's another copy of the temple, and so on. So fractals have occurred in man-made art since ancient times, and actually originating in India. Such fractals exist all through art all over the world. This is an example of a Fulani wedding blanket from Nigeria that's made in a diamond shape. And if you zoom in, you see more diamonds. And if you zoom in into those diamonds, you see more diamonds, and so on. M.C. Escher, a famous Dutch artist, loved fractals, loved self-similarity. If you zoom into this picture, you keep seeing copies of the same picture. So you can see this larger shaded region here, and then this region inside. They're exactly the same. One is just an enlarged copy of the other. It's, again, another example of man-made fractals. I'll end by showing you a fractal that occurred recently in Princeton. So in Princeton, we have a co-op where students get together and cook together. It's a vegetarian co-op, and every week they get a delivery of vegetables. And one week, one of the vegetables that came was this broccoli here, which is called, well, mathematicians call it a fractal broccoli. Because if you look at this broccoli, the formal name is Romanescu broccoli, but mathematicians like to call it fractal broccoli because if you look at this broccoli and you look at one of the horns on this broccoli, it's just another copy of the broccoli. And then if you look at one of the horns on that little horn, it's another copy of the broccoli, and so on. And so this is a fractal broccoli. And the students, when they got this delivery that week, this was about a year ago, they couldn't get themselves to cut it and destroy this beautiful fractal structure. And so instead what they did is they took that fractal broccoli and displayed it on the main dining room table. And hundreds of students that week, actually thousands of students that week, came and visited this shrine to fractals and came and ate there and looked at this amazingly perfect fractal broccoli. And that's the kind of thing that makes a mathematics teacher so happy, so encouraged, so inspired, that the students took the time and took the energy and took the mental effort to say, I want the whole campus to admire this mathematical structure. And this fractal broccoli, clearly, like the oranges that my mom used to buy when I was young, this fractal broccoli had a clear application, namely dinner. And yet they decided that it had an even better application, which is to teach the campus about mathematics and fractals. So I want to end on that. I want to urge everyone to look for patterns all around you, all around us. They exist. Be inspired by them. That's what we mathematicians do. I thank you for your attention. Thanks very much.